Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Thermal Oxidation from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, to know about the importance of thermal oxidation. Second, to learn about the working principles of thermal oxidation. Third, the two processes of thermal oxidation, that is dry and wet oxidation, will be discussed. Next, the theoretical model for thermal oxidation of silicon wafer will be discussed in detail. Lastly, the significance, structure and properties of silicon oxide will be discussed. So let us start with the basic introduction about the module. In semiconductors, manufacturing, the term oxidation is used to refer the conversion of silicon to silicon dioxide. This can be done by different methods, that is by thermal oxidation or by electrochemical oxidation. In IC technology, mainly thermal oxidation is used. So here we will learn the details of thermal oxidation and also about the theoretical modeling of thermal oxidation. It is important to note that the deposition of silicon dioxide, for example by CVD, is not called as the oxidation. Thus the term oxidation is used only for converting the existing layer of silicon to silicon dioxide. Thus, it is a modification process. So, we take silicon and modify it to get silicon dioxide. In that sense, it is similar to doping, where N-type or P-type material is added to silicon and modify it. So silicon dioxide is often referred to as the oxide and occasionally as silica. Now, what is the importance of the oxide? In the CMOS transistor, the oxide is an essential component. In the gate, it is called as gate oxide. Thus, it is the essential part of the structure. Second, it is used for protecting the silicon surface. Thus, it's a passivation layer. Silicon dioxide is actually a glass. The only difference is the normal glass that we use for making bottles or glass beakers, they have lot of other materials contaminants, whereas the pure silicon oxide used in semiconductor applications is of high purity. It is a good insulator and thus it is used as an insulator between the wires and between the transistors. Thus, it is also an electrically essential part of the chip. In some processes, it is used as the sacrificial layer. Why thermal oxidation? Thermal oxidation is one of the most common technique for the fabrication of micro-thin film of oxide, which is mostly silicon oxide on the surface of silicon over the surface of a substrate. This process takes place inside a diffusion furnace in between a temperature range of 800 to 1500 degrees Celsius. Though thermal oxidation is an excellent technique for growing silicon oxide layer for silicon substrate, it is not so effective for gallium arsenide, as thermal oxidation of gallium arsenide mostly results in non-uniform and non-stoichiometric film. This kind of film is not able to either provide proper protection to the semiconductor surface or provide electrical insulation. The oxide layer grown from thermal oxidation process, specifically on silicon, is useful as a passivation layer, protecting layer basically, insulating layer, and acts as a hard mask for nitride etching or as a sacrificial layer for surface micromachining or for drive-in diffusion process. Types of thermal oxidation. Now, following these are the types of thermal oxidation techniques that are used for the growth of oxide layer. First is rapid thermal processes, RTP. Second, diffusion furnace, horizontal or vertical. Third, RTP can be used to reduce the thermal redistribution of impurities at high temperature. Next, we have for smaller devices, this is an important consideration, and as a result, most engineers make use of low temperature processes. However, in rapid thermal oxidation, the thick oxide films cannot be produced, as it may generate stress in the film. Thus, for higher thickness, diffusion furnace process is preferred. Diffusion furnace based thermal oxidation. Now, this figure shows the schematic of a 3-zone oxidation furnace that can be used for making silicon oxide thin film over silicon wafer. The growth of the oxide film is governed by the diffusion of oxygen into the substrate silicon wafer, which means the film growth is actually downward into the substrate. So as the thickness of the oxidized layer increases, the diffusion of oxygen to the substrate becomes slower, leading to a parabolic relationship between the film thickness and oxidation time as shown in the figure below. The temperature is raised to 800 to 1100 degrees Celsius in 3 different zones to speed up the process. The center zone is naturally limited to materials that can be oxidized, and it can only form films that are oxides of that material. So the gas is purged into the thermal furnace from one end. This furnace is surrounded by resistance heaters, which produce the heating effect and are coupled with thermocouples to monitor this heating. This furnace is supported by ceramic supports having comb-like structure. The gas filled in from one side is vented out from the other side through the end cap, which is provided with a vent hole. So thermal oxidation of silicon is accomplished by placing the silicon wafers vertically in an open-ended quartz tube. The quartz tube is placed in a resistance heated furnace at 900 to 1100 degrees Celsius. So the process of thermal oxidation is divided into two categories. First is dry oxidation and second is wet oxidation. So as we have discussed before, the thermal oxidation, the process consists of two processes, dry oxidation and wet oxidation. So let us first discuss the dry oxidation. Dry oxidation, in this process, the oxygen gas is exposed to the silicon wafer at approximately 1100 degrees Celsius or above. The salient features here is that this oxygen is dry, that is, oxygen is provided directly without any contamination of water. So a very high quality oxide is produced using dry thermal oxidation process, which is described in this figure. So for devices such as MOSFET, normally the dry oxidation method is used to procure the oxide thin film. The chemical reaction for this process is very simple and can be described as Si solid plus O2 gas gives us SiO2 solid. So one major disadvantage of dry thermal oxidation method is that the growth speed is very slow. So let us now discuss the wet oxidation process. This process involves the burning of hydrogen and oxygen in their purest form at a temperature as high as 1100 degrees Celsius. This reaction leads to the production of a water vapor rich atmosphere in the oxidation furnace. This vapor then acts on the surface of the silicon substrate, which is in the form of a thin wafer, producing the silicon oxide layer as shown in this figure. And as you can see that the chemical reaction for this process is very similar to the one in dry thermal oxidation. That is, Si solid plus twice H2O gas gives us SiO2 solid plus 2H2 gas. So though wet oxidation method gives a comparatively faster growth rate, but the disadvantage is that the quality of thermal wet oxide produced is not so good as obtained from dry oxidation process. This technique is mostly used to produce the oxides that can be used as a masking layer or as a sacrificial layer for the process of surface micromachining. Chlorine oxidation. Now, other than the previously discussed methods of thermal oxidation, that is dry and wet oxidation, another method is the thermal oxidation process is to use oxygen rich in chlorine content to oxidize the thin silicon wafer. This method is popularly termed as chlorine oxidation or Cl oxidation, and the chlorine rich oxygen is produced by flowing oxygen through any of the chlorine containing compounds such as hydrochloric acid HCl, trichloroethylene TCE, trichloroacetic acid TCA. Also, sodium ions are introduced in order to improve the quality of the thermal silicon oxide film. This leads to the reduction in mobile charges and also decreases the amount of crystal defects in the silicon oxide film, hence giving us a high quality pure side layer. So the below figure describes the chlorine oxidation process. So students, let us now discuss a theoretical model for thermal oxidation of silicon wafer. And the model is Dgroove model, which is used to understand the formation of silicon oxide thin film over the surface of silicon wafer. Now the model describes the oxidation reaction occurring at the interface between the oxide layer and the substrate silicon instead of the reaction between the oxide and the ambient gas. So the most prominent model is described in this figure. So here, when the oxidizing species, which will be oxygen gas molecules, in the case of dry thermal oxidation, and water vapor in the case of wet thermal oxidation, interacts with the surface of silicon wafer, it leads to the concentration of the above mentioned species to reach C0 molecules per centimeter cube. The value of C0 is approximated to be 5.2 multiplied by 10 to the power 16 molecules per centimeter cube for oxygen molecules in dry thermal oxidation. So, when the temperature of the furnace is maintained at 1100 degrees Celsius and the pressure is applied is 1 atmosphere, the value of C0 at same parameters for wet oxidation process for water molecules is approximately 3 multiplied by 10 to the power 19 molecules per centimeter cube. So the Dgroove model can be divided into 3 parts for better understanding. That is, first, the transportation of oxidizing species from the bulk of the oxidizing gas to the outer surface of the oxide layer, as shown in this figure. Second, the transportation of oxidizing species across the oxide film towards silicon. Third, reaction of oxidizing species at the interface with silicon wafer and form a new layer of SiO2. So now, once the silicon oxide layer is formed on silicon wafer, the oxidizing species, oxygen or water vapor, starts diffusing through the oxide layer. This diffusion leads to the concentration of oxidizing species at the surface of silicon, which is denoted as Cs as shown in this figure, and the flux value for diffusion can be expressed as F1 equal to D multiplied by dC by the derivative of C with respect to X, approximately equal to D multiplied by C0 minus Cs divided by X, where D is the diffusion coefficient of oxidizing species and X is the thickness of the silicon oxide layer. Now the value of flux at the surface of the silicon wafer is F2 equal to K multiplied by Cs, where K is the surface reaction rate constant. So now from above two equations, F is equal to D C0 by X plus D by K. So the growth rate of silicon oxide layer is given as dC by dt equal to F by C naught equal to d C naught by Cs divided by x plus d by k. So solving the above equation, we get the silicon oxide relationship as x square plus 2d by k multiplied by x equal to 2d C naught by Cs multiplied by t plus capital T. Here, this capital T is the total time for oxidation, and it is given by d naught square plus 2d d naught by k, this whole multiplied by Cs divided by 2d C naught. So, after time t, x is equal to capital D by k multiplied by root of 1 plus 2 C naught k square multiplied by t plus capital T divided by dCs minus 1. So, for a small value of t, x is approximately equal to C naught k multiplied by t plus capital T divided by Cs. Whereas for a large value of t, x is equal to root of 2d C naught by Cs multiplied by t plus capital T. So, as can be seen from the equation, for small value of t, the thickness varies linearly with time, but as time progresses, the thickness versus time graph takes a parabolic curve as evident from the above equation. Oxidation rate factors. The rate of thermal oxidation first varies linearly with time and then eventually takes a parabolic route. Other than time, there are many other factors which affects the rate of thermal oxidation growth of silicon thin film. Few of them are orientation of the crystal. As we are well aware that silicon, being a crystal, has various crystal orientations, and the growth of oxide film varies according to the crystal plane, or rather than the orientation of the crystal plane. So, next is the oxidation method. Different oxidation techniques lead to different ambient environment for oxidation. So, as mentioned above, while only dry oxygen lead to a slow rate, using hydrogen in the wet oxidation technique or chlorine along with the oxygen increases the rate of oxidation. Oxidation rate factors. So first we will be discussing here the concentration of dopant. Doping of silicon substrate is recommended to enhance the oxidation rate. So if a substrate is doped heavily, the doping of substrate induces electric effect which weakens the strength of the oxide bonds, making it easy for the gas to penetrate through the oxide layer to reach the substrate surface. So heavy doping of substrate enhances and accelerates the rate of thermal oxidation of oxide film. Next is pressure. Pressure of the gas plays a major role in determining the rate of oxidation. So if an ultra thin layer of oxidized film is required, then the process is carried out at a very low pressure. Also, oxidation temperature gets induced significantly at a very high pressure. So as mentioned above, after a certain period of time, the oxidation rate becomes parabolic And this parabolic rate constant directly depends on the partial pressure of the oxygen used. So evidently, pressure plays an important role in determining the rate of thermal oxidation. So now students, the question arises, why silicon oxide? A shallow layer consisting of native oxides is formed easily on the surface of silicon even at room temperature, hence making silicon a good candidate for oxidation material. Silicon oxide plays a significant role in MOS technology. It is also strongly resistant to most of the chemical which are generally used for the processing of silicon wafer. It acts as a barrier for impurities and dopants, safeguarding the purity of silicon wafer. This highlights the role of silicon oxide as a masking layer. Silicon oxide is stable at higher temperatures, has a wide band gap, very high dielectric strength, and insulation abilities. This, coupled with the easy fabrication of silicon oxide, has resulted in masking the silicon oxide, the most desirable candidate for making a passivation and protective layer. Structure of silicon oxide. So silicon oxide in the general grown as amorphous. It has 3D tetrahedral network. So we have one silicon atom, it is surrounded by 4 oxygen molecules as shown in this figure. Now, since the oxygen atoms they are shared in a tetrahedral, a few times known as bridging bonds, and sometimes the oxygen atoms have non-bridging bonds. The non-bridging bonds leads to fused silica state, form quartz. Also, in hydrogen atoms can exist as impurities in the SiO2 structure, especially for wet thermal oxidation. Also, sodium and other dopants can also exist as impurities. So, the distance between the Si and the O molecule is 0.162 nanometer, while Si-Si bond distance is 0.31 nanometer. So, let us now discuss the properties of silicon oxide. As discussed earlier, the silicon oxide layer acts as a passivation layer and a protective layer. So silicon oxide has many attractive properties such as, first, excellent electrical insulator, that is, it has the energy gap of 9 electron volt and resistivity is around 1 multiplied by 10 to the power 20 ohms centimeter. Second, high breakdown electric field. It can rise as high as 10 megavolts per centimeter. Third, stable and reproducible Si-SiO2 interface. Fourth, conformal oxide growth on exposed silicon surface. Next, SiO2 is a good diffusion mask for common dopants. That is, if you are comparing the diffusion rate in silicon and silicon oxide, we get the diffusion rate of silicon oxide is very much less than the diffusion rate for silicon. It has a very good etching selectivity between silicon and silicon oxide. So now this table lists some important properties of silicon oxide. So students, let us summarize what we have learned in this module. First, in this module, we have established the importance of the oxide layer in many devices such as MOSFET. Second, though there are many ways in which we can achieve this oxide layer, but the one preferred by most is thermal oxidation method. Third, silicon wafer is cleaned and kept in a thermal furnace which can go up to the temperature as high as 1500 degrees Celsius. Next, this oxidation furnace is then subjected to either dry oxygen, that is dry thermal oxidation, or water molecules, wet thermal oxidation. The molecules of oxygen or water, they react with the silicon surface, forming a thin oxide layer gradually. Next, this oxide layer acts as an insulating material and can also be used as the protective layer. It is used for surface micromachining, acting as the sacrificial layer. Next, we also discussed the requirements for the quality of oxide layer that we can choose either from dry or wet thermal oxidation. Lastly, the configuration and applications of silicon oxide layer were further discussed in this module. Thank you.